Welcome, everyone. As you guys already know, I'm Tina Burns, and welcome to my dissertation defense. So what we're going to be talking about today is basically how we can classify or identify different parts of communication devices using machine learning or neural networks. Now, not all the networks that I have are actually neural networks, so it's actually different types of classifiers, but we'll get into that a little bit later. So there's going to be a few terms that you hear throughout the presentation: automatic modulation recognition, network traffic classification, and then the supervised and unsupervised ways of classifying these different devices and the different things within the communication spectrum. So all of this work is based on papers that I've already completed with additional information. So two papers were published last year by IEEE. One of them being a DBSCAN conference, and another one for a computer networks conference. We just submitted another paper for GlobeCom that I'm hoping will be accepted, but that's in review now. So this is a combination of those along with some additional information that's not in those particular publications. So let's talk about why I'm doing this research in the first place. As you all know, we all use some sort of technology device, right? When we're looking at this information, we have a series of things that we're using to communicate. It could be our Bluetooth speaker, it could be our laptop, it could be our telephone, it could be our computers. And that's only increased within the past few years because of the pandemic and a lot of people working virtually and a lot of companies offering, hybrid, the ability to work hybrid or to work from home. With this increase in the advancements of technology, it does present its unique problems. Researchers estimate that traffic, meaning network traffic, going back and forth over Ethernet, is going to increase by at least 1 zettabyte per year. That's 1 trillion bytes of traffic increase per year. And that's only expected to go up year after year as we advance in these technology spaces. Now, the issue with that is that it does present some unique things to address. One of them, of course, is slow connection speeds. When you're trying to go online, you have these slow internet connections, or you may have issues uploading, downloading information. You have the speed issues when you're trying to stream things, etc. In addition to that, it can actually overwhelm servers if there's too many people trying to access that information at one time, or there's a high data load requirement. It could overheat servers, etc. This increase in data traffic could also cause some websites to crash. And there's also privacy concerns. So typically when we visit a website or we go online, we expect or we hope that nobody's spying on our data and nobody can kind of tell what we're doing, although we know that's not really true. For example, a lot of people may use DuckDuckGo to hide their searches because they don't want Google coming in and having all these ads. What we'll show from this research is that might not be the best method, because even though there's ways to encrypt data, there's ways to hide your IP address with VPNs and et cetera, it doesn't really prevent the neural networks from determining what specific website you're on. So with all of these concerns, right, the overloaded servers, the slow speed in internet connections, and the privacy concerns, what can we really do about it? What you'll see in this graph here is that if you had something, you can think of a network system working as you have your host that's going to send out information. It's going to go through these devices, and then you're going to access this. You're going to access the internet. Now, if it could feel like there's a server's going to get overloaded, if you can identify the information and where that's coming from, you can actually delegate that to perhaps a different server, or you can send it to a different direction. But the first step to that is knowing where that particular thing comes from, right? So you take the host, basically after you get that, you measure the traffic to determine what's going through and where the information is coming from. You have some sort of sentinel or some control mechanism that says, okay, this is a particular device, I think will be best on this server. So now you can reallocate that or resend that to a different device or a different path on the server and prevent those congested links. Now, the applications of network traffic classification, they vary. You can use it to detect firewall breaches, right? If I know somebody's accessing my network and they shouldn't be, I can use this identification process to determine what it is and where it's coming from. I can look at it to find anomalies. If I feel like a server is getting overheated, I can look on that server, see where the traffic is and kind of what's causing that to be overheated or overwhelmed. You can also use it to help with monitoring and routing and planning resource usage, and also looking for new methods to kind of hide or protect your data. Now, that's just one aspect of this communications, the communication piece that we're talking about. So that's for network traffic. But what about the devices themselves? In addition to that, I'm sorry, some of the related works in this area are shown here. There's a bunch of research already on using neural networks to identify particular device, particular traffic, but we are doing something a little bit different with our research. So as we look at network traffic, there's also something else to consider, and that's the devices themselves. So when I talk about these cell phones, laptops, everything that you're using, these are all working wirelessly, right? So when we look at these devices, there's an estimated that there will be at least 13.8 billion devices that were added to the wireless spectrum in 2021. And it's great to have these advancements and all of the things that are here. But the issue is that if you'll see from this graph here, this blue line represents the allotted space or the allotted radio spectrum for these devices, for these wireless devices. This orange line represents the growth in those particular devices by year. If you'll notice that even before 2020, the amount of spectrum needed by the devices actually exceeded the amount of spectrum that was allotted by the FCC. So that creates a problem where now people are fighting and vying for that radio spectrum space. So then the question becomes, well, what do we do? Well, before you talk about what we do, there's something that the impact that it has is similar to the network traffic being overloaded. You can overload the cell phone towers. You saw that happen during 9/11, where everybody was trying to call at a particular time, and the cell phone towers literally just got overwhelmed and weren't able to complete those calls. In addition to that, sometimes you'll have like drop calls, you'll have interference from other things. And again, there's privacy concerns, particularly for the military, because if the military wants a dedicated radio spectrum and there's only a certain amount of space that's allocated, what will happen is now the commercial, those commercial companies are going to kind of infringe onto that military space, which means now they don't have that dedicated spectrum that they would prefer to have. So what do we do? Well, one of the ways to mitigate this is through spectrum management. That means basically I'm taking this radio spectrum that I have and I'm using it wisely, because although the spectrum seems to be all used up, it's not actually being used 100% all the time. So if I know what devices are available and I know what devices can cooperate and kind of work in the same spectrum, I can use that information to do dynamic allocation, saying, okay, this device and this device can both work on the spectrum at the same time. And since I know this is not being used, I can allocate that to something else. So in order to do spectrum management, you're going to need a couple things, right? You're going to have to do spectrum sensing, meaning I'm monitoring that radio spectrum, right? And when I'm sensing it, that means I need to figure out what device is being transmitted and received, or transmitting and receiving. And the one main thing for identifying those is automatic modulation recognition. Once I identify it, I can make a decision on what I want to do and then share the spectrum with other devices. And so this AMR technique, this is where my research comes in. Now, there's already a lot of applications that it can be used for, right? I can use this if I know what the device is. Like I said before, I can use it to determine what spectrum it goes to. And I also can use it to identify whether the devices that are trying to access my network or trying to access my tower are registered or unregistered on my particular device, right? So that has some security implications in there. Also, we can use it to determine if there's unwanted devices that are trying to access this particular your particular site. Now, there also has been a bunch of research done on this as well, and you can find out more about that in the paper. So let's talk a little bit about my research contributions. Whereas we're looking at this, we're looking at related work, right? A lot of related work has been done in automatic modulation recognition and using neural networks to classify them, and they've gotten pretty high accuracy. Same thing in terms of network traffic classification. A lot of work has been done on it. what makes my research unique is that I'm using the same networks for both network traffic classification and automatic modulation recognition. You'll hear me going back and forth between these two things because they're really two separate paths. And most of the time when there's research, people either focus on AMR or device identification, or they focus on website traffic. So my research is unique in that I'm using both of these, or I'm looking at the networks across both of these spectrums to determine whether or not we can create this Swiss Army knife of networks that can look at multiple features within the communication spectrum. In addition to that, I'm identifying websites using only the packet timing and the interval time and length information. Now, this is very, very important because what you'll notice is typically a lot of research that has been on network traffic classification has more features, right? They're looking at the payload, they're looking at the header information, they're looking at timing and a bunch of other features. And some of that information may not be available, right? If you're saying I want to look at the data payload, but the data is actually hidden or it's encrypted, then you're not going to be able to use it as a feature space. So we intentionally only use a small feature space in order to determine if the networks will be able to identify individual websites with just the timing information. Now, the timing and the packet information is always available. You can just sniff on like an Ethernet cord, and you can get that information in terms of how the packets are being sent and transmitted. You may not be able to access that data, but you'll always be able to get the timing and the packet information. In addition to that, I'm looking at the networks on a deeper scale, and I'm considering both the timing and resource information. I'll also look at 10 classifiers. Rather than just looking at 1 or 2 or 4 or 5, I'm actually looking at 10 different classifiers for these particular sources. So let's get into these classification techniques. Now, first thing I want to know is that there are 2 ways to classify data. One way is called supervised learning or supervised technique. And I'm being very specific and saying, not calling everything supervised learning, but supervised classification techniques are going to have both this, the X data, right? That's these little animals here, along with your Y data or your labels. And you're feeding that into the network, this network here, and you're creating a predictive model. So based on my label data, right, I know what the data looks like. I also know the label I want to assign it to. Now I can take unlabeled data and basically assign it to some label because I already know what those labels are. For unsupervised learning or unsupervised classification techniques, what happens is you're only given the data itself without any labels. And based on the data, you feed that into a neural network. And after it goes into this neural network and some sort of predictive model, then it can go into a clustering algorithm, and it makes those clusters itself. So it creates those classes based on just the data that you've given without any labels. Now, the benefit of this is that there's a lot of information that's available that you may not know where it comes from, right? A lot of website information, a lot of general information that you don't necessarily know where it came from or what's in it. So by using unsupervised network, it gives the opportunity to classify this data with less information. So let's go into some of our supervised classifiers. Now, remember I said that not all of them are neural networks. So the first classifier that we're going to talk about is actually a match filter, which is not a neural network. And the match filters are common. They're often used in like signal detection for like radar and other applications. And we wanted to use that in this particular instance to kind of compare how those neural networks stack up against kind of an industry standard. The way it works is, let's say I have a known signal, I have an unknown signal. I'm going to send this through this process, which we're calling cross correlation or convolution, and then I have a threshold. If the output of these correlations is above that threshold, then I'm going to make a decision to say that it is part of the class. If it's not, then it's considered not part of that class. So what you'll see is, if for my implementation in the networks, I used a bunch of signal templates, right, to say, okay, I have all of these designs or all of these maps for my different signals, and I'm going to test. I'm sending all these test signals. I'm going to convolve them, and for each one of these, so these are my 4 modulation schemes here. For each one of these, I'm going to use Bayesian inference to determine whether or not these are part of the class. So what that means is I'm going to have a threshold that it meets, but based on how well it performed with the previous classes, I might assign one class above the other. And then the predictions are output of that particular classifier. So this is not a neural network, but the next one is, right? So neural networks, you're going to have three components. You're going to have something called the input layer, right? That's my X data or my images. If I'm trying to, determine, hey, is this a cat or a dog? This is what you're feeding into the input layer. The second one is going to be where all the work and all the weights are done. That's called your hidden layers. And then you're going to have something at the output layer. For the fully connected network, what makes it different than the other networks is that if you'll see here, these are the nodes or the neurons for the network. Each node here is connected to all the other nodes in the previous layer. That's why it's called a fully connected or dense network. So for our fully connected networks, here are the layers that are listed here. There's two networks that are pretty much identical. The FCNN and the binary network are basically the same, except for the output. For the fully connected network, it takes a class and it chooses between all four outputs. For the binary, it chooses between two. So it's either a yes or a no, and it has to run n times in order for it to make the full classification. Second network we're going to talk about is the convolutional neural network. Now, whereas it does have some of these fully connected layers at the end, the main part of this convolutional network is that instead of it just using a neuron or using those connected nodes, it actually has a kind of like a 2D map that it uses to convolve against other layers, and that is used to determine the weights associated with that particular layer. Now, CNNs are extremely popular and they're very effective in general for neural networks. We've seen that really used even with identifying images and other things. So they're very popular and they're very effective to the point where a lot of people, when they do research, they only consider CNNs while excluding other networks as well. A long-term, short-term memory network. This one is a little bit of an older network and it's not used as much, but it's a recursive algorithm. And one of the benefits of it, maybe benefits and disadvantages, is that rather than just being looking at one form of it, it's called a feed-forward network. It's not a feed-forward network, but it's recursive. And that means it can take information from the previous layer and feed it back into the current layer that is being looked at. So that's pretty beneficial, because rather than having just one thing that you're looking at, you're actually making it so that you can feed the information or gather the information from the previous thing. So these have been known to be really effective for example, time-sensitive data. Now, our LSTM network is actually pretty shallow, and I'll talk about why in future research. So our last supervised neural network is the autoencoder. The autoencoder is actually, we use a bunch of these connected nodes, and what's unique about this is it can be divided into three portions, really, two separate portions, the encoder and the decoder. What the encoder does is it compresses the data into smaller bits and creates this bottleneck right here. And then the decoder receives the input and basically reconstructs or recreates the data. The benefits of that is that you can take this information that has a huge data space that's really, really large, and you can make that smaller and just pull out the significant features rather than having this, slew of data. You can use this to kind of pull out just what is important in those. The autoencoders are really good at denoising images and creating stuff with a smaller feature space. In addition to that, because of how they operate, right, because I can use this just to recreate the image, it can also be used for a basis for unsupervised learning. So our autoencoder is kind of designed here, what you see in there in terms of the layers. But speaking of unsupervised learning, here are the classifiers that I deal with for my unsupervised networks. So the first one is something called k-means clustering. And what I'll say is that in general, when you're dealing with your data, you have to figure out how you want to cluster that information, right? So with the unlabeled data, if it's just given here as a raw data, the final output would be this. And the way the k-means clustering works is it starts off from the initial points. You have a number of clusters that are selected, meaning you know how many classes you want. You're going to create a center point, and then you're going to add each of those. You're going to assign each data value to a particular point. And then after that, you reevaluate those centers and then repeat the process again until basically those center points stop moving. If you do have a question, feel free to let me know. Now, self-organizing map is another clustering algorithm. Instead of it being point-based, it's basically a map. So it's using the information that it has to take your input data here and cluster it according to the map. For this, the nodes in the map, these guys are changed each time it gets input data. The third type of clustering is called a DBSCAN algorithm. And what you see here is how it kind of works. It takes it's density based, meaning if these are grouped together very closely, then I'm going to put this in the class, right? Because even though this might be kind of over left and right, what it's really looking at is how dense this information is in terms of whether or not it's going to be in that particular class. So it starts off with the point, you cluster it, and you keep on adding and adding and adding to that cluster if you have things that are near it that are dense towards that. Once you have everything added to a cluster, then you're done with the algorithm. Now, recall that before I said for your unsupervised learning, it's a little bit different than supervised, right? So you start off with training data, you send it through an algorithm, right? For me, that ends up being this autoencoder. And then once you have the new input data, you're sending it through through a predictive model. That's right. I'm going to go ahead and try to read this. You send that through this predictive model, and then after you have the model, you can send that through a clustering algorithm, which is we talked about here. So our two networks with those that are using anything that has an AEU before it has both this autoencoder and the clustering algorithm. But the other two models only work by the clustering algorithm themselves. All right, so let's talk about how we generate this data. First thing is for the automatic modulation recognition, the way we generate the data is we basically have create a computer simulated data for it with 4 modulation schemes, and then I output it to a binary file which has a certain format. So there's 2 types of data that I have. The synthetic data and then the over-the-air data. So the over-the-air data, which is in the grid, those are actually information that I received from things that were transmitted from software-defined radios. So I take this synthetic data that I've generated with the noise information added, send that through a transmitter, receive it at the other end, and that received data becomes the grid data. Now, for the grid data, what you'll see here is a picture of kind of all the transmitters that were in the lab where I'm testing it. So what I did is I chose 4 transmitters and 8 receivers and used that in different configurations to get the information. Now, the distance for that ranged from basically from 3 feet to 70 feet because I wanted to see the impact of what would happen if I had longer times of transmission. For the network traffic classification, what we did here is we take a computer that is one of them, I think they're located at the Hill Center at Rutgers, and we're sending and receiving information via the internet, and we're monitoring it on this Monex port. That's how you collect all the data, you send it in PCAP files, and you get the information. So the way we generate the traffic for the web data is actually through a script. We use Puppeteer, and it basically cycles through a bunch of sites, and then we collect the data, the packet information from those sites, monitor it, and then basically format the data appropriately for the networks to be able to receive it. So we're thinking about the different classes that we're using. I'm actually looking at 10 different websites, and we wanted to have a variety of websites, some being informational, some being just, people that they're just going to visit, shopping and different things, and some being news-based websites to kind of have a variety of these different sites and see where that would lead in terms of data. So what you'll see here on the left is kind of those class labels that I designated for that particular data, and then on the right, the actual websites. All right, so now let's get into the results, which is probably my favorite part. All right, so I will say that originally, when I was asked to do this project, and we were like, oh, we're going to use just the packet timing and length information to distinguish websites. I was like, this is not going to work. I didn't think that it was enough information because there's a vast amount of information that's available. And I didn't believe that just with that, you could actually detect the websites. Well, my theory was incorrect. And we did find that with just the packet timing and the size information, you're able to predict with very high accuracy which websites you're visiting. So what you'll see here is a graph showing this is the accuracy of the actual website, and this is the number of websites. So I use like this sequence to say, okay, I'm just going to start off with 2 sites, and then I'm going to keep on increasing the number of sites and see how the networks perform. Now, as expected, as those number of classes increases, right, as that increase the amount of information or the amount of classes that the accuracy decreases as well. Now, the best performing network is this convolutional neural network here in purple. The other network.
So I just want you to clarify a little bit what the 2 axes are. So the number of websites is the number of websites in the training set. So the network has to accurately predict at 10. It means if it was guessing, there'd be a 1 in 10 chance it guessed correct.
Right.
But you're seeing here that the average accuracy looks like 80% or something.
Right. So, just above 80% for the network. Yeah. So this is, as you increase the number of websites, you're going to see the change in accuracy. What you'll also notice is that the LSTM performs pretty poorly, even as it goes along. The FCNN and the autoencoder are kind of in line with each other, but you'll notice that as the number of websites increases, the gap between the convolutional neural network and the others actually increases significantly, right? Whereas here, it probably looks like it's about 10%. When you get here, there's almost like a 25 or 40% difference in terms of accuracy. So we'll see that not only is the CNN network better at overall classifying it, but it also is not as influenced by the number of classes increasing. Number of websites increasing, excuse me. Now, what I was looking at here was accuracy, meaning out of all the data that's sent, how much am I predicting correctly overall? But if you want to look at the classes themselves, meaning the website themselves, you need different metrics. So for that, I'm looking at something called precision, accuracy, and recall, or precision accuracy, precision, recall, and the F1 score. So if you look at information kind of in this graphical format, where I have true positive, meaning it was predicted as this class and it belongs to this class, true negatives, it's not part of that class, and it was saying, no, you're not part of the class. But then also the false aspects of that here, you get what's called a precision score. The precision score is basically the rate of true positives, meaning out of everything that I have classified, out of all the information that I've given, how much of that is it really saying is part of the class, and how precise is it in giving that data? The other part of that is what's called the recall. Now, the recall is going to take into factor those false negatives. So am I saying this is part of a class, or this website belongs here, when it actually doesn't? And depending on the data that you're working with, you may want a high precision score or a high recall score. Now, if you're looking at the classes themselves, you don't want to just look at the accuracy. You want to look at something called the F1 score, which I relate it to as like the accuracy for individual classes, and that will tell you really how well the network is for each class. So given that, what you'll see here in this graph is the precision, accuracy, precision, recall, and F1 scores for the websites. Now, some of them have really high values, right? So if I'm looking at kind of like the Britannica, NFL, Yahoo have high accuracy, have high values overall, whereas some of them are really low. CNN is a little bit harder to detect than the other ones, You'll also notice that not all of them have the same level of precision or recall. Some of them have higher levels of precision, meaning that I'm going to be more accurate when I tell what belongs to this class, whereas the other ones are better at telling things that don't belong to this class, right? And it varies. So for the CNN, for the New York Times, actually, that's a good example. It has a pretty decent precision score, but its recall is pretty bad. So that brings it down its overall accuracy. Whereas for the Britannica website, it has a lower precision than it does a recall score. And that combined kind of gives you the overall accuracy of the particular network for the website. Now, another thing we wanted to look at and investigate is what happens generally, like the more information you feed neural networks, you would expect to see some sort of increase in the accuracy level. So we started off with a small sample of data or a small number of packets and increased that. And we wanted to see what would happen to the accuracy level as we did this. And you'll see that it's kind of climbing up. Now, this is a linear regression curve for what will happen as a projection as we continue to increase that data. And what you'll see is this is not a perfect fit, but you'll see that this convolutional neural network, and actually none of the networks have reached a point of their highest accuracy. Like if we continue to increase the number of packets in there, we will probably get higher accuracy levels here on that one. The LSTM is still pretty bad, but the other networks might have time to grow. Now, the amount of data that we collected ended up being 20 million packets per file or 20 million packets per website. So that's a total of 200 million packets if we consider all that for the training data, and then also another set of 20 million packets for the test data. So now, with that being said, there's also this is for the website data. In addition to that, we also looked at the automatic modulation recognition. So remember, my first class that I talked about was actually the match filter. And what you'll see here is that for all of these classes, it has this blue line represents for the match filter how accurate it is for all the classes, but the two modulation schemes are actually lower than the others. And we believe that that's because, well, the match filter is doing this prediction. What happens is it has to go through this correlation value. Once it correlates the information, it takes whatever is the highest value from that output, and that's the class that it assigns to. What you'll see here is that even when I look at a QPSK signal, which is in red, sometimes when I match it with another signal for an APSK, that APSK is going to give me a higher output, which is why the match filters will have a lot more false positives, and it makes it harder for it to predict the data. Now, I'm giving that as a precursor because what you'll see in this graph here is that as we're looking at these different elements, the match filter is actually pretty low compared to those other results. And although it's an industry standard, the way we're using it is a little bit different. And because we have kind of those false positives, that's why the accuracy level is pretty low. So at 244,000 samples, you'll see, again, the convolutional neural network is performing pretty highly. These other networks, though, basically all the other networks are just slightly behind it, except for the LSTM, which has this huge gap between what's being sent and what's being received. If we look at the grid, right, so this is the data from actual receivers, what I'm actually receiving over the air. When I look at the grid data, you'll really see that difference between both the CNN and these other networks, right? You see a wider gap between the convolutional network and these other ones, as well as a really big gap between these networks and the match filter and LSTM. And again, LSTM is performing, pretty poorly. But you'll see that from my synthetic data, remember the synthetic data, the same data, all I'm doing is I'm sending that I'm transmitting that to a receiver. So it's the same data only transmitted over the air, and you see the difference in how those networks respond, which tells us that the networks themselves are sensitive to those real life events of multipath and fading and whatever happens when that information is actually transmitted over the receiver.
Yeah, do you want to explain? Can you explain the x-axis a little bit? I think there's people in the audience that don't know what SNR is. So intuitively what that is.
X-axis is called the signal to noise ratio. So anytime you send a signal, right, you're going to have the actual signal at a certain level and then a noise floor, right? So your noise floor is all the unwanted stuff that you don't really want to see. If I want to see my signal that's up here, I don't want to necessarily see the noise or interfering signals here. So my signal to noise ratio is a ratio or a comparison between that. The higher the SNR, that means the higher the signal is above the noise floor. When that becomes lower or when that becomes closer, that means your noise is becoming higher and your noise is becoming more powerful than the actual signal. And the way we do it is in decibels.
So what's zero? Yeah, go ahead.
The zero means that your signal and your noise are at equal levels.
Right, because it's log. Yeah, I guess for the audience, it's log scale. Yeah. Okay. Was there another question?
Yeah. Also, Tina, can you repeat what you said about multipath?
Yes. So, so multipath fading. Where is it? Okay. So the data that's being sent here is my synthetic data. So keep in mind, this is just the data that I generated with these modulation schemes in GNU Radio. And this second graph is that same data transmitted over the air. I have additional plots in here that I can kind of show, but there's, when you transmit it over the air, you're going to get interference, you're going to get signals that are coming back and forth and have like kind of this multipath fading where the signal may fade in and out. And if that happens, what you receive is going to look a little bit different than what you transmit. And from a network perspective, it's going to make it harder for them to distinguish between those different interferences. So another thing we looked at, of course, was the timing. Remember I said that for the LSTM is the worst performing networks, but it's also the most shallow, meaning it only has a couple, it just has a couple layers. And the reason for that is if you look at this in terms of timing, right, this LSTM takes a lot more time to train and to test than the other networks. The fully connected network is actually the quickest network in terms of all the evaluations here. And the LSTM and the CNN both have high in terms of timing, but that's why those layers are limited. With that being said, this is a summary of kind of how those networks are looking. If we look at the CNN, you'll also see that CNN has a lot more parameters, right? So we're looking at something that basically has 16 million parameters as opposed to the LSTM, which has 12,000 parameters. So somebody asked actually in the proposal, given that this has so few parameters, what would happen if we normalize the networks to have, the same amount of parameters, right? So I actually did that for this test set. And what you'll see here is that same GNU radio set that I had before. I sent these through normalized networks. And what that means is I decreased the filter. The network kept the structure, but I decreased the filters or the number of nodes until I got to a point where it was closest to the lowest number of parameters here. So this 12,804, the networks here are tested with that. And with that, you'll see that the other networks actually, the LSTM, if the other networks had the same level of parameters or they were normalized, the LSTM kind of comes into comparison with it, and at the higher SNR is better given those particular that normalization. But the convolutional neural network, even with fewer parameters, still exceeds all the other networks. So yes, the number of parameters does make a difference somewhat, but apparently not as much for the CNN network. And what you'll see here, this is a comparison of those normalized networks, right? All of them are just over 12,000 parameters, 12,000 edges. And what you'll see is the LSTM still takes a really, really long time to train and test. And even a fully connected network, right, which takes about 3 minutes or less than 3 minutes, still has relatively high accuracy, right? Higher than the LSTM. And it takes a lot less time to train. That's also an important note because if you're considering what network to choose, you may not want to go with the convolutional neural network if you're concerned about resources, right? If I want to get the best result possible at the fastest time, there may be a trade-off between this fully connected and the convolutional neural network, depending on the data set that you're working with.
So I have a quick question here. So looking at the CNN line there, so if you decrease the size of the CNN to 12K parameters,
right, this guy right here,
versus, and the accuracy there was 84% at zero SNR.
Yep.
And then if you go back, what was the accuracy? Was like 10% higher at 16 million or something?
Yes.
No, it was 100%. Okay.
100%. I probably should have did these in the same order. I don't know why I didn't.
Well, okay.
Yeah. Right. So you're looking at about 15% change in the accuracy level.
Right. So then if you go back to the graph, can you go back to the graph?
Into this guy?
I'm just trying to eyeball where 84% would be for, not this graph, the full size network.
This guy. Oh, I see. So the 84% is probably around here. No,
it's got to be, the full size network. Where's the accuracy results for that one?
So this should be
right there. Okay.
Yeah.
Okay. All right.
So this is the full size network. And if
kind of eyeballing, it looks kind of like -8.
Yeah, that's probably about right.
Okay.
So it pushed it over maybe about 8 dB, I guess.
Okay. So if I'm willing to reduce my network size by, that's pretty good. Yeah. Roughly a factor of 16 million, or well, not 16 million. Let's say it's 10K versus 16 million or something. So that's still kind of order 3 or 4 orders of magnitude.
Right. So if you do reduce your you're still going to get high performance. You're just
still going to get right. It may be so on a very tiny device, right? I might not be able to fit 16 million parameters in a really small device, but definitely 12K I could. And,
right.
The accuracy doesn't collapse actually, which I would have thought it does, but this is pretty.
I thought I didn't know it would be well, but that's actually still pretty good.
Well, because you're shrinking the network by this enormous amount. You would think the accuracy would collapse, but it doesn't. So
like orders of magnitude. Right? 12K from 16 million to 12.
Yeah. So okay. All right, thanks.
Can I ask something?
Yes.
The multipath, was it the same when you were testing and training? Or it was
yes. So both of them, when I'm testing it, they're both tested in the same environment at the same time. So basically, I create a test file, right? A train file. I stop the not the computer, but I stop collecting the data. And then I run it again to collect the test file. So they're collected like in that same time frame with, maybe a couple seconds different, not even a couple seconds because it's really fast in terms of how it collects it, to make sure that all the data has kind of the same parameters. Did that answer your question?
Yeah, but multipath would change the result if it was different, right? In a real world scenario where you collect data from different sites, the multipath will be different.
Yeah, so let me, I'm actually going to unhide that. Here's why I believe that part of it is multipath fading. So originally when I started this, I was anticipating that as we increase if you're only looking at the signal and the noise, right? As you increase the distance, you're going to get more attenuation essentially, and your signal essentially is going to decrease, right? So I would expect based on that the networks would have better performance at the lower distances. At better performance when the transmitter and receiver are closer together. And the reason I said that I believe that multipath fading is playing a factor in it is because you'll see from this graph, right? It doesn't really, even if I have a distance of 70 feet, right, which is represented by this blue line here, it's still on par with it being basically at the same accuracy level if I had 3 feet. And that's a little bit weird to kind of see because I would expect that with those being so far apart that you would see the difference in terms of those accuracy levels. And in the same aspect, this is for the fully connected network. This one that is at 45 feet is kind of in between, but it actually has worse performance, which I believe is due to some of those multipathing, that multipath figures, right? Because it's kind of in the middle of the network. So it's getting different things in that particular signal, which is why I believe it's lower than the other one, as opposed to it being 70 feet.
Yeah, so if you go back one slide, right? There, right there. So I mean, I think the first multipath result you're showing. The multipath results, or not multipath, but the inside the orbit room distance results, I guess. I think you were definitely saying that there, but especially is Rich Howard on? Yeah, he should be here. Well, go keep. No, not this result. You have the distances in the orbit room slide. You were just talking about it.
Yeah. So this
right there. Yeah, this one. So this one I think illustrates it pretty well. Right. In Rich Howard always this thing that you get in these multipath holes or a really bad radio spot, and this illustrates it pretty well because, right, the accuracy at 70 feet is just as good as 3 feet.
Right,
and the accuracy is not correlated with distance, which means that you're probably in some kind of bad multipath spot for that particular node. Right?
So yeah, as opposed to it being like, okay, it should be 3, 23, 35, and kind of go down the line. Right. It's this random like 45 feet being the lowest.
So the most plausible explanation is that the multipath effects are dominating here rather than distance effects. Yeah.
Another one would be perhaps the receiver itself, but that's a little bit far-fetched.
Yeah, that's pretty far-fetched. It's possible, yeah.
I tested it for each of those receivers, and if it's at 6 feet, meaning if I'm transmitting with something really close, they still have pretty high accuracy. So basically, it's not going to be a receiver. Now, to add to that, so we see that FCNN are fully connected. Now, the LSTM, though, is very sensitive to these different distances. The only way that the LSTM predicts is actually with 3 feet. Every other distance is just like, no. So I mean, it also depends on the network itself. And I guess the LSTM in particular is sensitive to those distances, the difference in distances.
Can you hear me, Tina?
Yes.
Oh, good. Okay. I was having trouble with that. This was 2 questions I had. One of them was, with the CNN, with all those parameters, if you actually look at the parameters after you train it, are you removing parameters in a random way or by removing the parameters that don't matter? Well, how many of these don't matter? Is it a zip fly? Is it a power law kind of distribution where just a small number matter?
Yeah. So the way that I changed it is I kept the number of layers. So each layer has some sort of convolutional input. And that actual convolutional factor, it has something called filters. So what I did is I kept all the layers there and I literally decreased and made the filters smaller until my number of parameters got down to 12,000. Okay. So it has the same structure, it's just that the number of filters I decreased.
But the filters are based on the magnitude of the parameters? I mean, if the parameters are close to 0, they don't matter that they're there.
When you say parameters, are you talking about the actual input parameters?
Yeah, the coefficients in the weighting coefficients in each of the nodes.
Those parameters are going to be determined by both the filters and the number of layers, right? Because each time.
Well, yeah, I think the question is, did you train the network, get the weights, and then cut the network down based on the weights being very low, in which case they don't matter? Or did you just somehow have an algorithm that before you did any training, cut the weights out? I mean, I guess that's the...
Okay, I get the question. So what I did was, yes, I did. Basically, I trained it on a small set of data, a small data set, and I trained and tested, and I decreased the layers literally by just looking at each of those and kind of look at the output of the parameters themselves and the accuracy as I was running the test. So rather than running it on when you have these parameters, whether you have 10,000 data points or you have 1,000, the parameters in the network itself, because they're associated with the network, are going to be consistent. So what I did is, because I know it's going to be consistent, I started off with a small data set and I basically trained and tested on that small data set while decreasing the number of filters until I got to 12,000. 12,000.
Okay. Right. But there was some amount of training to start. So it wasn't like you just by randomly picked it. Okay. So
No.
so I guess that gets at Rich's point, which is there's a lot of, in a trained network, a lot of parameters don't matter, even if it's a little bit of training, I guess. So it seems to.
And the second question I would ask, Tina, is this is really nice. You're looking at the, the dependency for a fixed data set on the architecture. But there's another parameter which is interesting, and that is if I increase the data set size, which one of these approaches gets better faster? I.e., which one makes the best use of data?
That's a good question. I would say that I would not do that with the LSTM network because there's a factor of timing and resources, right? So for the LSTM, although it has these small level of parameters, by the time you increase it, because I originally tried that, you're increasing your testing time by days. So you got to balance kind of, the time along with those, the number of parameters.
I know for some of the CNNs that are used in the autonomous vehicle programs, if you add more miles of exposure, it very sublinear improvement. So some of these architectures might be much better at using new data than others. That would be worth looking at some point if you have.
I think that would be a good factor for the fully connected, because the fully connected is already so fast. I could potentially add a lot more layers or a lot more parameters to see how well that performs. But that would be the one that I would vote on for doing that.
Well, it'd be nice just to take your data set, divide it in half, and do all this again with half the size of the data and see which ones get worse faster. You can always cut the data in half instead of adding twice the data. Get a slope.
Now, are you saying data or are you saying parameters?
I'm saying data. Take these exact networks, train them on less data, and see which ones break down faster. That'll give you an idea, if you added data, which one would get better faster.
Now, we've already kind of seen that. I don't have it here, but we did do it with like a smaller data set, 244,000 samples versus 2.4 million samples. And I do have the information for that.
Okay.
And you'll see that the LSTM does get better with more data, but the time, of course, is just pretty bad.
Good. Thank you.
All right, I do want to. So we haven't gotten to the unsupervised yet. So I want to just get to the unsupervised networks. So for the unsupervised networks, right? If I look at it, so what you'll see here is this is representing. I'm comparing this first one on the left-hand side are my supervised classifiers. I'm looking at data, a very small subset of my modulation data. So what I basically did is I took 4,000 samples for modulation, right? 1,000 from each modulation type. And I just looked at that in terms of those classifiers. And the unsupervised neural networks did not perform well at all. So what you'll see here for my SOM, my AE SOM, all these are below 50% just for that small set of data. And the reason I did that is because these three networks here, when I tested it, the k-mean actually takes a very, very, very long time to train. I didn't even have time to finish running all of it. So I wanted to see kind of how it would perform for that smaller subset of data. I will say that given when I trained these networks, I created synthetic data and was able to get pretty high accuracy with that synthetic data, up close to 100%. But for these particular the real world sets, it did not perform well for that information. And you'll kind of see that here, right? If I look at these three unsupervised networks, the only one that has a little bit of accuracy, which is kind of weird, is the DBSCAN algorithm here with kind of this hump here. Now, I will say that I use a series of learning rates and different neighborhood functions to get what I believe was the best values for the DBSCAN, but there can be further research that's done on kind of optimizing these networks, meaning if there is more time spent on these particular networks, we could probably increase the accuracy of those as well. When I look at 20 million packets, again, the DBSCAN is better, barely, than the other networks. But what you'll see is the networks basically under here aren't classifying at all, right? If I have two networks and I'm classifying with 50% accuracy, excuse me, that basically means that it's guessing, and the neural network really can't distinguish between what that particular information is. All right, so what does all this tell us? One very important result from this is that neural networks can identify websites with only the packet timing and length information. So if I just have the length and the timing information, I can use that to distinguish between websites. So it doesn't matter if you hide your IP address, doesn't matter if you encrypt your data, it doesn't matter if you're, if you have something that's, protecting it from us seeing the data payload. With just sniffing over that Ethernet, that line, and looking at just the packet and the timing, the networks can predict your particular website with really high accuracy. As the number of as the number of packets increase, of course the accuracy of the networks increase. The CNN overall has the best performance, but the other networks can provide comparable accuracy. And as Rich mentioned, if those parameters were increased, we might actually see something that was closer to the CNN as well. The LSTM and match filter classifier are the networks that lag behind everyone else. And for this particular set of data, the unsupervised networks did not seem to perform very well. And what this tells us in terms of application is that if you really want to encrypt your data, meaning you don't want people to know what website you're visiting, it may require a more complicated algorithm to kind of obscure that data, maybe some sort of randomization of packet timing or whatever the case may be, to ensure that people cannot tell which website you're visiting. For future work, what can be done is perhaps testing the networks of websites, including more packets per website to see where that curve kind of dips off and levels out, and also improving the unsupervised learning approach as well. And that's all that I have. Did you guys have questions?
Yeah, so there's a public question session, I guess.
Yeah, and I can't pull up the chat. Oh, here's the chat right here. You can write it in the chat if you want to. I
have a question.
Yes.
So great work. Just wanted to comment on that first. The question, I think two related things. One is the LSTM. Why do you think the LSTM network performed so poorly, considering that we would expect that temporal information and that sequencing relationship would help, would give information about the underlying protocol that was being used?
That's actually a really, really good question. I believe that part of kind of the difference is that the network's not deep enough. I really think that, so all the other networks have at least 6-7 layers, right? It's a deep learning network. For the LSTM, I literally have 2 layers of LSTM, and that's it. And I don't think that gives it enough parameters to really get a good basis for detection.
So do you think that you could have, that perhaps for future work, you would try to compare your network so that they have roughly the same number of parameters?
Yes, which was one of the reasons for doing the neural network. So yes, I would say that would be future work. I would also try to just increase the number of layers in the LSTM. So I did read up, there are functions like in Python that you can use that will basically decrease your time, because really it was a timing factor. Like the LSTM literally took 3 days to test, whereas one other network would take like a few hours. So if there is a way to decrease the actual timing, then I would add more layers to that LSTM network to see how it would improve in terms of accuracy.
So a related note, one related thing, because I had the 2 questions and I kind of extended it. But anyway, and it's more of a comment. It's there was quite a bit of work, and there's still some interest in this notion of intrinsic dimension, which I would point you to, or perhaps where that would be interesting to look at. There's paper from 2018 called Measuring the Intrinsic Dimension of Objective Landscapes. And it's sort of a methodological contribution about how to determine what the sort of optimal number of parameters is in for any given network, given your data set. So I think that would go hand in hand with some of the stuff you've already done, and would also be a nice contribution.
But how does that function? I mean, how do you know what those optimal levels are unless you're actually going through a set of tests?
That's what you're doing. It's a methodological paper. So they show you sort of, how to increase the size of your network and graph it until you find the inflection point.
Okay. Cool. Are there any additional questions?
Yes, if I may, Tina. Umberto LaRoche with Cisco here.
Hi.
Hi. Quick question here. Actually, it may not be so quick, but I'm wondering, what does your research say about the nature of the internet, in that you can learn characteristics about traffic between AP just by looking at packet size and I guess, what was the other element of the feature vector that you looked at?
Timing.
Exactly. And then the second question is more of a comment. In my circles, this thing called Apple Private Relay created quite a bit of commotion in mobile networks when Apple introduced it into their iPhone devices. Mm-hmm. It's an attempt to obfuscate the detection and nature of the traffic. And I get the impression, I just want you to confirm it, that your methods here would tell you something about traffic despite Apple Private Relay being turned on. So why don't you take the first one and then maybe give me a quick answer to the second one?
So if I understand, the first question is, based on my research here, what does that tell me about identifying internet traffic?
About the nature of the internet, in that you can actually learn characteristics about traffic from point A to point B just by looking at a feature vector comprised of packet lengths and timing information.
I think that the one thing it says is that it's really, it's easier than you think to really be able to identify the traffic. Now, keep in mind, these are neural networks, right? So this is advanced, learning and getting all the information. But just even with a small set of data, there's going to be repetitions and patterns that those networks can pick up on. Even if there's, some sort of an encryption method, it's still not as encrypted or as safe as you think it is. I guess that would be my evaluation. As far as what Apple implemented, now these results are based on just individual websites. I would suspect that it could probably extend to other things like applications and different things as well. But even with just, if you're just randomly going to a particular website, I think that the networks at a minimum could still detect some of that data. Unless somehow you're hiding the packet length or timing information, it's still going to be able to make some inference, I would suspect.
Normally, you could just tell the source and the destination websites by looking at the IP addresses. Apple Private Relay just obfuscates that with a double-blind proxy scheme that they have. It's actually active on most of the recent iPhones. And it sounds like if I took Tina's technique here, I could figure out what websites people are looking at, even though, despite Apple's best attempt to obfuscate that information. That's my comment.
Yeah. I guess just to follow up on that, if you think about intuitively, right, these neural networks are incredibly good at picking up differences in patterns. And if you think about a website design, website A versus website B, where the advertisements are and the size of the font and, all those other parameters are patterns in the data. And what Tina's results are showing is that these neural networks can pick up on that as reflected in the networking traffic.
Right. It doesn't need to know the address.
Right. Or it doesn't even need to know, right? Those patterns are discernible with enough it's not even really that many, like sort of order 20 million packets isn't that.
Yeah, that I think is really significant. Thank you, and congratulations on your work, Tina.
Yeah. So what I want to follow up with the Apple thing is, Apple could add algorithms to, if it was kind of act as a proxy where it modified the packet sizes and timing, but they would have to. That's a lot more work. I guess that has a much different kind of proxy than most people.
It sounds like it's more trouble than it's worth, but who knows?
Yeah,
Thank you. Those are good comments.
Okay.
Thank you.
Wonderful. I had another question, but I think he's leaving. Looks like Martin has his hand raised, but I don't know if he still has the question.
Oh, I still do.
Oh, okay.
Hi, Tina. Fantastic presentation. I've actually had this question since you first told me about your research. To the other people here, I'm not an electrical engineer. I apologize if this is an ignorant sounding question. How difficult would it be to adapt this system to, say, a sound-based system in water? If you can transmit that data into something that neural networks can receive, meaning a binary file, it wouldn't be complicated at all to kind of to test it. Because one of the first things I started thinking about when you were saying different frequencies and bandwidths and such is fish actually communicate via sound, but they're all at different frequencies. So you might be able to track fish species using this, which would be incredibly useful. As your fun fact of the day, apparently the sound piranhas make is barking. But yeah, that was my question. Sorry.
No, you're good.
To ask a question? Yeah.
You hear me?
Yes.
I was going to just say that's very interesting, Tina. Very interesting presentation, and there's a lot that what you're doing here is very interesting because it takes what people have done at the physical layer. They can look at the physical signals like the modulation, the way the transmitter turns on, and they can identify unique transmitters this way because there's enough statistical difference. And what you're doing here is very interesting. I've never seen this before. You've taken and doing the same thing to the upper layers, which is seems very, very useful.
Mm-hmm. Well, that was one of the things I wanted to see. Like typically, that was one of the notes I wanted to make is that people usually do it in two separate spectrums, right? Or two different forms of research. But is there like a Swiss Army knife that you can use across that, across the communication spectrum, right? Can I use something for both devices, network traffic, and a bunch of other stuff with just the same network structure? And apparently it may be possible. All right, I'm going to, for my committee members, I'm going to open up a breakout room and you guys are free to head over there. If anybody else has additional questions, I'm free, I'm here. Questions or comments?